Even though Proxima b is only 4.2 light-years away, it seems improbable that we will ever make it there. This is especially unfortunate because, in addition to being the closest exoplanet to Earth, the celestial body is also thought to be habitable, which is especially unfortunate since we aren't even succeeding in taking over the planetary world that is right outside our door. One might think that interstellar travel in general will remain an unfulfilled dream forever, but it doesn't have to be that way. In fact, experts are currently working hard on the development of new propulsion systems that will soon enable us to leap to the stars and finally bring exoplanets like Proxima b within our reach. But what groundbreaking concepts are being discussed in this regard? How realistic is their implementation? And could Proxima b actually become our interstellar springboard? If anyone knows how to explore the vastness of space, it's the two Voyager probes, no wonder, because Voyager 1 and 2 have now covered incredible distances of 24, 6, 7, and 2062 billion kilometers between them and the Sun. This in turn corresponds to 165 and 138 astronomical units, and thus not even a single light day. This is estimated at around 173 astronomical units, and if we now consider that Proxima b is about 4.2 light-years away from us, we realize that the Voyager probes would have to fly another 70,000 years before they would reach our planetary neighbor. And at this point, it should be noted that the identical sister probes are by no means chugging through space at a leisurely walking pace, but are sweeping through interstellar space at around 61,000 km/h. Despite all this, the title for the fastest man-made object of all time does not go to Voyager, but to the Parker Solar Probe, which was launched in 2018 and reached a mind-boggling speed of more than 635,000 km/h in July of this year. And yet even this artificial Speedy Gonzales would need several millennia before it would arrive at the Proxima Centauri system. And, as we now know, the Aeonimus red dwarf in the Centaurus constellation does not travel through the universe alone on the one hand, and Proxima Centauri is part of a triple-star system which is completed by Alpha Centauri A, and Alpha Centauri b, on the other hand, also represents the central star of a planetary system that has at least 3 members, and in particular its Proxima b discovered in 2016 that repeatedly attracts astronomical interest, and that is not particularly surprising. After all, we are dealing here with a rocky planet within the habitable zone that achieves a remarkable value of 0.87 on the Earth's Similarity Index. To put it simply, the habitable zone is the range of distances that a planet must be from its host star in order for water to be able to dwell there continuously in liquid form. Does this imply that Proxima b is a cosmic twin of Earth? No, not necessarily, but one thing at a time. The Earth Similarity Index measures how much an exoplanet matches our earthly home in terms of energy flow, mass, and radius. Proxima b, with a mass of 1.17 Earth masses, is generally classified as an Earth-like exoplanet. But be careful, the term Earth-like refers only to rocky planets with solid surfaces, without providing any information about their habitability. And while Earth is known to take 36 to 5 days to orbit the Sun, Proxima b only needs a little over 11 days for one orbit. This is for the simple reason that the distance between the exoplanet and its host star is just 7 million kilometers, but that's not all. In fact, there is growing evidence that Proxima b has a tidy locked rotation, which means that it always presents the same side to its host star. Consequently, its surface is also divided into a bitterly cold night side and a significantly hot day side, and yet there would be a narrow strip between these two extreme zones that allows life to flourish. But according to our current knowledge, water is also needed for that development. And lo and behold, assuming the appropriate orbital parameters and suitable atmospheric composition, the expert simulations have shown that the cool wet stuff could actually be splashing around here in abundance. However, it should be noted at this point that we are dealing with a purely theoretical model, because in reality, many parameters that would be necessary for the existence of liquid Water have not yet been conclusively investigated, and then there's also the problem of radiation. Although Proxima Centauri, a red dwarf, only has about 12% of the mass of the Sun. It attracted attention a few years ago with an unprecedented radiation burst in detail. Researchers at the University of Colorado observed how the star increased its ultraviolet radiation for 14,000-fold. Within a few seconds, the monster eruption was thus even 100 times stronger than any solar flare recorded to date. And then there is also the fact that the eruptions on Proxima Centauri are not only significantly more intense but also much more numerous than in our home system. In view of this, the gloomy forecasts predict that the extreme radiation from the host star will sooner or later destroy the entire atmosphere of Proxima b and put an end to the development of life once and for all. And yet, there is a scenario in which the exoplanet can withstand the turbulent radiation bursts of its host star. To do this, it needs a liquid core that forms a stable magnetic field that blocks the radiation and prevents the oxygen and water molecules from escaping into space. Furthermore, it's conceivable that Proxima b is still drawing from its original water reservoir. One theory is based on the assumption that the planet actually originated at a much greater distance from its host star and was only later captured by it. According to some simulations, Proxima b once had 10 times as much water as Earth, and even if it had already lost 90% of it because of the intense star radiation, there would still be enough water today to support a massive ocean that would cover a significant portion of the planet's surface. However, because of natural subdivision, the water could only remain permanently liquid in the slender twilight zone. Will we ever reach Proxima b? The idea of interstellar travel would be more like a boiling pot during the day and freeze to ice at night. The two Voyager probes are powered by radioisotope thermoelectric generators, which turn the heat from the radioactive decay of plutonium into energy. However, as was previously mentioned, it would take tens of thousands of years for the two most remote outposts of humanity to reach the Proxima Centauri system. So what do you do when the outdated propulsion technologies have had their day? That's right, you switch to good old sailing. Yes, you read correctly, because what may seem like a rather dusty idea at first is actually the heart of the revolutionary Breakthrough Starshot research project. Breakthrough Starshot seeks to demonstrate that it is not only feasible, but also realistic to send a spacecraft to the realms of Proxima Centauri in 20 years or less. But how is that even feasible? How can the 70,000-year estimated travel time be shortened to such an absurdly short amount of time? Basically, when your ambitions are lofty, you occasionally need to take smaller steps to reach them. In particular, the project intends to send tiny probes, only a few grams in weight, into orbit. Their solar CS will then be illuminated by a strong laser from Earth, and the light pressure will quickly accelerate the mini probes to 20% of the speed of light, allowing them to accomplish the enormous starshot. Groundbreaking method for a small spaceship to reach Proxima b. Incidentally, the concept of using light sails to propel a spaceship is not new. In fact, American physicist Robert Forward first proposed it in the 1970s. However, this particular propulsion concept has certain unique requirements. To reach the necessary speed of 60,000 km/s and to be able to withstand the acceleration of several 10,000 g, the component's dimensions must be kept to a minimum. In particular, Breakthrough Starshot aims to create a microchip-sized spaceship that would only have a programmed control computer, a power supply, a camera, a receiver, a transmitter, and a solar sail. However, merely producing this technical is not enough on its own as mentioned. It also requires an Earth-based laser thrust in detail. However, it would require not just one, but a multitude of lasers that combine to form a 100 GAW beam and that target the 4-4-meter area of the solar sail 20 million kilometers away during the acceleration phase. If this is successful, a laser beam of just 10 minutes should be able to pave the way for the nano probe to Proxima Centauri. But doesn't this all? sound somehow utopian. After all, the tiny spaceship would then somehow have to manage to decelerate at the destination in time. Expressed in figures, the probe would have to decelerate from 20 to around 6% of the speed of light in order to avoid rushing past the star system of Desire within a few seconds now. In this regard, some researchers point out that it might be better to abandon the concept of a huge energy-guzzling laser anyway and use solar radiation instead. In this case, however, it would need a sail about 100,000 square m in size, made of a light yet robust material, such as graphene, in the same breath. However, natural starlight could also be used for the urgently needed deceleration. Maneuver: as soon as the probe is about 5 stellar radii away from the triple system, it could turn its sail around so that it's slowed down by the light of the stars in front of it. According to a computer simulation, the braking effect of the light combined with the gravity of the stars may actually be enough to allow the probe to swing into the system. However, this process takes time, and if the probe is also to reach Proxima b, a staggering 100 additional patients would be needed. In this case, the estimated total flight time is up to 140 years. It is currently impossible to predict which changes the researchers will make in the future or which variant they will ultimately select, and it will be a few days before Breakthrough Starshot becomes more than just a daring concept. In the not-too-distant future, humanity may succeed in IND by directly leaving its home system and studying exoplanets up close to study the subscribe button. Up close, you don't have to leave for strange star system. Press the thumbs up button. The scientists involved estimate that the development time alone will take 20 years, but it can already be said that the challenges of such a project can be overcome, at least on paper. And subscribe right now to ensure you never miss another one of our videos. We hope to see you soon,